Welcome everybody, I'm Claudio, this is Pawel, and today we're going to be talking to you about the new animation system that we have been developing for CRYENGINE in the last, let's say, 5 or 6 months. Let me give you a short overview of the talk. First of all, we're going to go through what we currently have in CRYENGINE, and we're going to explain why we decided to start from scratch and do something new. Secondly, I'm going to give you a walkthrough of our new modular animation system and the playable system. And I'm going to accompany the walkthrough with examples taken from a theoretical use case for setting up a complex character. And then at the end, in the second half of the talk, Pawel will present our animation graph functional DSL, domain-specific language. And he's going to go more into details into what model we chose for this and how the execution and the computational parts of it work. What we're not going to show today is live demos. Sorry if anybody was expecting that. We're still internally testing it, and I think you guys internally are going to see something very soon, but we don't have anything to show at the moment, so this is all still talk. So, contents of the talk, I'm not going to go through all of them, just so you guys get a mental model of what we're going to talk about. Just so you know, my part lasts for about 30 minutes, and Pawel's part lasts for about 30 minutes as well, and then at the end we have about 30 minutes for questions. Alright, so what do we have currently in CRYENGINE? First of all, we have a two-module system, right? So we have a higher level module called Mannequin and a lower level module called CRYAnimation. So Mannequin deals with all of the smart logic of playing animations. It's what we call a fat animation controller. Why we call it fat? Because it has like lots of complexity, lots of different features inside of it. It deals with transitioning from one animation to another, syncing multiple characters, creating these reusable setups. And then on the lower level, we have CRYAnimation, which deals with more of the computational aspect of creating a character pose. So it has a structure called the layer transition queue, which is able to set up different types of blends for characters and also deals with blend spaces and has a pose modifier system that allows you to plug in custom procedural animation logic. So this is a fairly common pattern in game engines, and we figured that it actually has some disadvantages, which we're going to go into. So first, let's look at Mannequin more in detail. So Mannequin has a set of features that have been used to ship numerous games, including Crysis 3, Rise Son of Rome, Hunt Showdown, both of our VR games, Robinson and Climb, and also Kingdom Come Deliverance, one of our licensees. And these features are very, very useful and allow you to create character setups that scale well when a game gets large. And all of these features are pretty much battle tested, and we know they work. We know they're good ideas, most of them. But Mannequin also has some problems. And first of all, when Mannequin was built and it was designed with the assumption that it was going to be the highest level system controlling animations. And so it allows the programmer to inject logic through this action system, but then the actions themselves are designed so that they can't be aware of each other. And what actually happens in practice is that you usually have a higher level system that is more aware of the overall character state and needs to coordinate the actions with each other. And thus, the actions over time tend to degenerate into simple animation containers. The second problem is that Mannequin delivers all of its features, and there are many features, into a single module with an all-or-nothing approach. And this creates many workflow problems, but also some problems on the back end where it's difficult to conceptualize and to maintain it and to expand it with new features. From the workflow point of view instead, the users usually are presented with this huge editor that has so many features, and it's difficult to start and just tackle it one feature at a time. The editor is also based on MFC, and we've switched to Qt in CRYENGINE 5, and there's a quite flimsy translation layer that keeps the editor running, but it's also started to be quite unstable. Lastly, it's not particularly easy to debug. It still relies on text printing on screen. It's not particularly bad, but we can do better. And as a last point, there's really no explicit way to add features to Mannequin. The only way is to refactor it or add stuff directly into the module. So we would like to make sure that in the future, if you want to extend, there's precise dependency injection points in which you can extend the system. So Mannequin was designed with this idea that you have a longer initial cost, but this brings about a reusable setup later on in your development cycle. The problem, though, is that the setup becomes static as you develop it. And so experimenting with the setup tends to become more costly. So you end up with these setups that you don't really want to touch because you don't want to break anything, and you just keep swapping in and out animations out of them. So this is where we decided to go with a new animation system to replace Mannequin. And so we start developing a new system. We got to figure out what the goals are. So the goals, first of all, we want to make sure that all of the good Mannequin features are still good features of our new modular system. So we want to salvage all of the battle-tested features that Mannequin has. For those that don't know what they are, we're going to go through them as we salvage them, as I explain it. These reusability features are very useful, and we don't want to lose them. So we don't want to end up with something worse than what we had before. Secondly, we would like to offer these features modularly with a workflow where they are only introduced as soon as you need it and not before, so that it helps with the learning curve, but it also helps with the modularity of the system. So if you want to extend it, you can also insert a new module in this framework, and they're supposed to work together. And this brings me to the third point, which is that our designers and artists can experiment cheaply with the system, even in late stages of the development cycle. Obviously, it's not that it's going to always be easy, and late in the development cycle, things tend to crystallize, but we just want to flatten the curve as much as we can. As a fourth point, we want to try to use modern graph-based editors because that's what everybody's going with, and it seems that they have some serious advantages in presenting complex information to non-programmers. And as we want to provide specific directed avenues for extending the system. So let's look at how the system looks from a high-level view. So we start, as in Mannequin, with an animation controller, but this one is thin. So he went to the gym and he lost a lot of weight. What does it mean? It means that the animation controller now doesn't deal with a lot of complex logic. It's just something that matches outputs to inputs. It just binds data together. And what is the data that it binds? Well, this is what we call scopes. So this is a term that we borrowed from Mannequin because we think it's pretty good. And scopes are basically just abstract layers, named layers that have a semantic meaning. So for example, your upper body motion, your full body locomotion, hit reaction. So they're layers that represent one aspect of the character motion. They can also just be parameters. So target for IK, right? Or target for gun. These scopes, we place them on what I call a state line. So the state line is just abstract, it's not an element of the system, but it's an approach that we're taking that we want to make sure that all of the stateful computation of our animated character is segregated, and we want to make sure that it stays on the left of this line. The advantages for this will be clear later in the presentation. So on the right of our state line, if the scopes are the aspects of the character pose, you can think of them as ingredients. And the animation graph is the recipe to get from these ingredients a final pose for your character. So this is a functional domain-specific language, and I'm not going to go too much into it because Pawel's part is fully on how it works. But the idea is that the animation graph is functional, and it has this property that purely functional computations have, which is referential transparency. And it means, in layman's terms, that with the same inputs, you always get the same output. And this allows us to do a lot of different types of simplifications of the graph, and also helps with the debugging and reproducing the state of animations if we want to debug or use it for networking. All right, so then we need to look at the left of the state line. And this is where the generic playable system comes in. If the animation graph is purely functional, is free of state, the playables encapsulate all of the stateful logic of our computation. So the playables are generally just pose producers. They're just objects that can produce either poses or a stream of poses or parameters, and they encapsulate all of the stateful logic of our computation. And finally, we have objects called motion maps that are injected by the animation controller. And motion maps are totally optional, and it's what allows you to bind abstract names to concrete playable assets. This is used to reuse a character setup among multiple characters. We're going to go through all of these elements one by one in a bit. So let's take a look at the playable system. And so we have these playable assets, and the playable assets are just what your tech artist or your artist will author in the end, or your designer. They produce a stream of poses or parameters. So with pose, we mean a pose buffer that contains the pose information of a character. With parameters, we mean vectors, transforms, quaternions, etc. And secondly, they can have multiple output channels. Now, the reason for this might not be clear right away, but we'll get to that later. And internally, the playables can be composed of other playables. So for example, a state machine doesn't really produce pose on its own. It just offers the pose produced by another playable that its internal states consume. So it can have internal logic that selects pose or blends pose between different playables and then just outputs a single pose, and then the scopes don't care about how that pose was computed. But the playables only contain the persistent data. It's like the part that you author. So we need a type of object that represents the data that you actually need at runtime. Because, for example, you might have a state machine, but you want to execute it in different contexts and have different states in those different contexts, right? So the sampler is just the actual instance necessary to use the playable. So it's instantiated from a playable asset, but you can have multiple samplers per playable asset. And it has two functions. You can tick it forward in time, and you can sample one of its channels. It also supports taking a snapshot of its state and restoring it. And for those of you that worked with networking, you know this can be useful for networking purposes, but also for just debugging purposes. All right, so we're going to run you through a use case. This is a theoretical use case, and we're going to use, as an example, a third-person character. And we're going to be using images from Rise, from Marius Titus. We're also going to be using some examples taken from Hunt, because some problems that Hunt guys had inspired the design of the system. So sometimes we need to take some examples from Hunt. We're just going to walk you through how you create a character setup with this system, how you start and what you end with. So you start off with a state machine. Everybody knows what a state machine is, so I'm not going to explain it. Basically, we're just switching between different animation assets, and in our move state, we have a blend space. And yes, obviously, we want to provide a node-based editor, which is going to be based on the state machine editor that's being developed by Interactive Systems. And the state machines are simple. They're user-friendly. They're easy to think about. But they have a few disadvantages. They tend to scale poorly with character complexity. The main two modes in which they tend to scale poorly is when you try to add quality or variation to them. As you want to add quality of transition, so you want to add an intermediary state between idle and move, for example, or maybe you want to add different types of move depending on the context, whether you're crouching or wounded. And these combinations of states tend to explode rather quickly and go into very high numbers, turning the state machine into a huge bowl of spaghetti. So actually, we would like to change the state machine layout as infrequently as possible. And this is something actually Mannequin is pretty good at. And we just want to take some features from Mannequin and make sure that they're also offered in the new state machine system and that they help us with scaling the state machine up. So the first feature is tags. Tags are simply variations of a state that you can add without changing the overall state machine structure. So you mark your character with tags. And tags are just strings. Obviously, internally, we'll process them as CRCs for performance reasons, but overall, they're just strings. And a character can have any set of them. And when you request a state, the best matching implementation is selected and executed. So this is actually not the same thing as a hierarchical state machine, because the tags are evaluated non-strictly. So they're evaluated on a best fit basis. So even if you don't have the exact same combination of tags, you will always get something out of your state, as long as you have at least one implementation. You might think, well, this is not very useful because I want the exact animation, but how is this useful? Well, it creates flexibility in workflow, where, for example, your designers or programmers can add new tags to the gameplay system, and you still don't have implementations for them. Well, your character will not break. It will simply play whatever animation it has that it best matches those tags. On the other end, if your animation team creates animations and adds new tags onto the state machine, and these tags are not being requested by the gameplay systems, they will still be there and it will not break the game, right? So you have a flexibility in how you want to approach adding variation to the character. And obviously, if you have some options that are equally ranked, we can choose them randomly, we can choose them according to some gameplay logic. So the other main thing that people want to do with state machines, they tend to want to make the transition from one state to another look good. And how this is usually traditionally done is to add another state in the middle. But actually, if you know what you're doing, you know that this is actually not how you do it, because you need a state for each direction. And as these scale up into all of the possible transitions that you have among all of your states, then this starts to become very, very unwieldy. So how do we do it in CRYENGINE? Well, this is another feature that comes from Mannequin, and this is going to become a theme because, well, most of the features that we are presenting as modules, we are borrowing from Mannequin. Whenever a state is requested, the animation that's been marked as transition gets executed at the beginning of that state. but the higher level state machine doesn't know anything about it. So when you request an event, you request a change of state, the state machine appears as already being in the target state. But internally, you use a rule-based system similar to the tag system, where it matches the state names and the tags currently active to try to get the best transition that it can. And if it doesn't have anything, then it will just proceed to do a linear blend. All right, so now we have a character, and the character is moving around, is jumping, moving, whatever we've set up in our state machine, and we have also figured out how to make it look nice when you transition from one state to another. We also have variation for gameplay context, so when the character is wounded or crouching, etc. Now we want to add something more. We want to add some motion, for example, some attacks for our third-person character that only play on the upper body. Maybe you want to add procedural corrections like IK, or secondary animation. Maybe the character has a ponytail, or has something attached to his vest, and we want to animate it using procedural logic instead of having the animators author this. Maybe you want to correct the foot placements of the characters as he moves around. Or maybe you want to add some details using additive animation, for example, for breathing. So what do we do? Well, I assumed from the start that our character was going to have only a single scope. So a single scope just means that you have a single input of the character that can consume playables, and that input just gets piped as a final pose. And this is how you would find your animation graph when you first start editing it. That's the default state. It's just one input, one output, no operation. If we want to do something more, well, we can add these scopes to the graph. So scopes are generally, as I said, inputs to the animation graph. They're the ingredients of the recipe, and they're named layers that control different aspects of the character pose. So the scopes are what consumes the samplers of the playable system, and they can consume either motion, so character motion, streams of poses, or different types of parameters. The scope itself also handles simple blending between samplers, so not complex blending or transitions, but it will do linear blends between the samplers as you switch between them. So the scopes are the ingredients, the animation graph is the recipe, and the animation graph, as we said, is a consumer of pose inputs and wants to produce a final pose. So we create this animation graph. We're going to talk more in detail about how it works later. And the animation graph gets authored against a skeleton, so you can set different rules for like masking specific joints, for example. And this is a purely functional stateless domain-specific language, which allows us particular benefits that we're going to see later as well. So let's see in a third-person character how you would create your scopes and how you would bind the playables to scopes. And this is a very simple example. I know that it actually gets much more complex than this. Obviously, we're just trying to get a high-level picture of how it works, right? So we have these character scopes that control different parts of the character animation. And we also have some a blend space for the character to look around, and then we want additional IK correction, so we also pass the target through game code. And then at the end we have some additive details, which is done through a breathing animation. So with the first few scopes are controlled through state machines. So these are complex actions that need to react to gameplay events. But the other ones are just controlled directly by a blend space. So this is what shows you can actually only plug into the scope the level of complexity that you need for that specific scope. So you don't need to be running on the highest level of complexity all the time. And for example, for the last scope, which is just an animation loop, we can just have a gameplay system that selects different animations at random and just plugs them into the scope. And we don't need anything more. So to summarize what we have right now, we have a high-level locomotion state machine. We have the ability to adapt to gameplay context, and we can influence different parts of the character body. We can also do procedural corrections to our character and control them to gameplay code. So what do we do now? We have, let's say, a full character. So the problem now is we need to create a new character. And when we create a new character, we would like not to repeat this work. This is one of the things that Mannequin is pretty good at. Like, a lot of people hate working with Mannequin because it's very complex, but once you've done the work, actually creating a new character is not a big deal. As long as that character has the kind of same gameplay concepts and is a gameplay equivalent to the original character. So what we would like to do as well in this case is just to have new assets so that our art and design team can add new assets, but to reuse the high-level setup so that we don't have to change the gameplay code at all or change it as minimally as possible. So this is where the motion map feature comes in. And this is just a map between names or IDs to concrete assets. It's a map that can be swapped at runtime. So if you switch a weapon, you pick up a weapon, you pick up also the whole set of animations necessary for that weapon. And you can also just use them to represent whole different implementations of the same abstract motion set, for example, for different characters. And the great thing about motion maps that makes them different from other types of animation remapping in other engines is that they also will contain the implementations for the state tags and transitions. So this means that you can have a generic state machines with only the high-level states, and then each character can have their own implementation of the tags and transitions. And where this is useful is, let's say you're creating a new character, you don't have time to create all of the animations for all the possible variations, you just implement the basic motion set, and you can have the character running around and working in the game. Obviously, it's not going to look the best because it's not going to react to some gameplay variations, but more or less it will work. And then you can progressively add what's missing. So this is helpful from the workflow point of view. The problem now with the motion maps is that what happens in Mannequin is that you have to create your fragment map at the beginning, right? So we would like to avoid this. So what we do is that we allow the user to easily export a state machine out into a motion map. So all of the stuff you set up in your state machine can be exported into a motion map, and then the state machine just becomes a high-level generic set of states, don't have any implementations. So you can separate your state machine into two parts, basically, and then for this you can create additional motion maps in parallel to this original motion map, and you can swap them in and out. All right, so we figured out how to make different characters with the same setup. Now our last problem is how we coordinate characters with each other. So in this case, a kill move from Rise, let's say. So we have two characters they need to execute the same animation at the same time. Or maybe if you are a pacifist, maybe you want them to be friends. So here they are shaking their hands. Another problem in coordinating different characters is when you have an object held by a character, which might be a skeletal mesh. And in this case, in CRYENGINE, this is a character. This is also a character. And we need to coordinate them with each other so that the animation that you play on the gun exactly corresponds to the animation that's being played on the player. So this is what the animation controller does. And the animation controller only does this, only coordinates animations. So it's a coordinator layer, and it just binds the playables to the character scopes, or at least the individual channel outputs of the playables to the character scopes. And we will see right now why it's useful to have multiple channel outputs for each playable. So an animation controller can control multiple characters, but also multiple animation controllers can control different parts of a single character. So this allows you to flexibility in what part of your character you relinquish to another animation controller. Now the question is, what kind of playable do we plug in so that it can be executed on multiple characters? Well, that's a timeline. So the timeline is equivalent to the right pane of Mannequin, if you have used Mannequin. And it's what allows you to put playables on different layers so that they're executed at the same time. And the important thing is that these playable channel outputs are bound to the scopes automatically by name. So if you have a good naming scheme, the binding will happen automatically. You won't have to think about it if you have a good naming scheme. Now, you can override this, but by default, you won't have to set up complex binding maps or other stuff like that. So let's look at how a timeline would look like in the abstract sense for a kill move animation. So you have a first layer of a player playing a kill move animation, and then a second layer playing the animation for the death of the enemy. Another case is for the reloading of a gun. You can have the reload animation on the player and the reload of the gun on the weapon. But this is not the only things you can do. Maybe you want to play multiple animations on different scopes of the same character. This is actually something Crytek did doing Climb. Right? So Climb has his setup like this, or similarly to this in Mannequin. So we can use a base layer with a base pose, and then we can do the different details of the animations by using additives on different scopes. And this is very useful for detail animation, for example, for hands and stuff like that. So as our last point, the timelines also allow you to annotate animations with gameplay events. So for example, sound effects, loading magazines, or other types of gameplay effects like reloading, shooting, etc. Additionally, you would be able to also set up specific time zones where something is active or inactive. And this works similarly to the procedural clip feature from Mannequin. Finally, what I said at the beginning, we need to have a good way of extending the system without complicating ourselves too much. And this is going to be easy through dependency injection. You're going to be able to implement these these interfaces through C++ if you want to create your own kind of pose producer. And this is going to be very, very useful in the future. Right now, we're just trying to get what we have, encapsulate it, modularize it, and provide it to you in a more usable way, in a way that you can think about it more easily. But in the future, we're going to want to add more features to this animation system. And the great thing is that if you create samplers, basically, that they can be plugged in scopes, or they can be plugged into a state machine exactly as native types. And this will allow us to create plugins such as motion synthesis, done with like machine learning, linking to DCC applications such as Maya, and just piping them into character scopes by just writing plugins. And our clients, our users, also will be able to write their own plugins if they want to do some custom type of post-production. All right, so I've talked to you about the modular animation system, and now Pawel is going to talk to you a little bit more about the animation graph domain-specific language and how it works.
Right. Hi, my name is Pawel, as most of you already know. As Claudio mentioned, I'll be going a little bit more in depth about the animation graph, which is the thing that Claudio already introduced on his handy infographic. This is the purple part. So I'll try to briefly cover maybe not that briefly, but I'll try to cover what the animation graph is and exactly how it came up to be. It is essentially a visual scripting tool that has been conceived as a CRYENGINE's general push towards better accessibility and empowering designers and artists to be better exposed to certain features of the engine. It is a low-level component of our new animation stack, which essentially means that it interfaces features related to mostly combining motion and procedural motion adjustments. Its role in the system is to consume playables to synthesize the final character motion that's actually output on the character. So it basically means it serves as the backend of our new animation stack. So it handles all the number crunching, workflow management, multi-threading, and so on and so forth. So Claudio already covered the high-level controller features, Mannequin, and basically the features that we are trying to salvage from there, or the features that we've been inspired with the design of the new animation stack. I'll try to briefly cover what the low-level features are that we'll be replacing. So the low-level animation stack consists of layer transition queue, which already has been mentioned previously. It's a pretty simple layer-based structure. The general idea is that it consists of a couple of layers that you can queue animations in. Then each layer handles transitioning between clips which are playing, doing stuff like synchronization, time warping, and whatnot, just to match source and destination clips. So this is the temporal transition parts. On top of that, it also provides means of vertical blending between layers. This just the standard linear override, additive blending, whatnot. But the cool thing about it is the fact it also allows to plug in what we call pose modifiers in between each of these layers, and pose modifiers are responsible for, essentially parametric pose corrections that can be plugged in into arbitrary point. Since I already mentioned it, we have this pose modifier framework, CRYENGINE. This is what we use for procedural corrections of motion. We ship the engine with a bunch of building blocks like IK solver constraints and whatnot. Like most of you who work with it are already familiar with it. But the cool thing about the pose modifier framework is that it's extensible through dependency injection. So for instance, game coders or like third parties can extend it by implementing no pose modifiers and provide them either through plugins or through game code. It's a very handy feature. It's very liked by game programmers because it allows them to hack in that animation feature that they need to ship by tomorrow without touching the engine code and actually be it executed as a part of the engine internal loop update. So we went through a couple of case studies when we actually realized that we can't really build up on what we currently have, and we will try to salvage features and build and provide a new architecture from scratch. One of the case studies was the initial locomotion setup for Hunt. I know how many of you know about it, but Hunt used to be in the initial design of TPP action shooter. And back in the day, we used to have a very creative technical artist working on it, Matthias Lindner, and he basically introduced an experimental setup for TPP locomotion, which essentially consists of a base layer playing only a single pose, and then everything else was like additives on top and procedural corrections. So he used layer transition queue to implement that. For that purpose, he needed C++ because the feature itself is not really exposed to the designers, but it was fine. Like Matthias wasn't really scared of C++. But the problem is the fact that the layer transition queue wasn't very flexible as a structure to implement this particular setup. So how he dealt with it is he hacked it in. And I had the opportunity to actually review his changes, and at that point I realized that he basically implemented that blend tree, like within a blend queue. And he was like, Yeah, essentially I did. So that left like a long-term impression on me. And at the same time made me think that TechArt probably shouldn't have to go with this if they want to come with their experimental setup for a character, right? And I also figured out that you probably need some sort of outline tree. Yeah, this was essentially a point when we realized that the layer transition queue is not flexible enough for us to serve as the basis for the new animation stack, especially if we want to enable extensibility through different plugins, which might be producing arbitrary motion. Right? What were the initial requirements for our animation graph? Well, first of all, it needs to be a solid foundation for the animation stack, obviously. At the same time, we want to empower designers with more control over how corrected pose is being evaluated. We want the post modifier framework to become more accessible because it's a really powerful feature and we'd like people to experiment with it a little bit more. And at the same time, while for kinematics, skeleton animation is our primary use case, we don't want it to be married to it. We want the system to be flexible enough to handle animating other stuff such as morph targets, material properties. At the same time, the current implementation isn't, I mean, the layer transition queue isn't terrible, but yeah, we can definitely do better. So after laying down the requirements, what we basically need to realize is that we're not simply designing a tool, we are designing a language. So we started our design process by researching existing solutions in the market. What we noticed is that the fact they tend to contain a lot of hidden unmanaged state. Like, for example, when you're working with animation graphs in Unreal, it oftentimes happens that you have some sort of like a state machine which is hidden within your graph and you need to think about it constantly, and it's not very easy to like reason about it. To reason about how the graph is being evaluated. It makes it hard to track what's actually going on. And at the same time, the other thing that they do is they tend to apply very general computation techniques to very domain-specific problems, which makes them unnecessarily complex in many ways. And at the same time, they don't exploit certain computational properties of the problem to squeeze out like more performance that could have been squeezed out. Next, what we need to do is identify our domain. So the domain for our language is essentially motion synthesis, which is combining animations, combining poses, combining character animations, and correcting them. At some point, I had that realization that what you're essentially working with, especially on low-level stuff, is just a special case of signal processing. All right, so let's explore a couple of paradigms that are friendly for motion synthesis or signal processing in general. Well, the first idea is to use data flow programming. This seems like an obvious match because data flow programming essentially emphasizes the movement of data and models the whole program as a series of connections and how this data interact with each other, how it's being transformed as it progresses through the graph. So it's a really powerful tool. There's a bunch of solutions out there that have been used to good success for solving similar problems, both signal processing in general and also motion synthesis. Well, Unreal being a good example. And DPP borrows quite a bit from functional programming, which made us thinking that since we're already starting off of something, since we already want to use functional programming to a certain degree, but at the same time we're annoyed by a lot of hidden unmanaged state. So what we can do is try to push this idea further because we see potential benefits, and we ended up with this idea of maybe trying to introduce a purely functional DSL and see domain-specific language and see how it will tackle these problems. Claudio already mentioned what purely functional means. It basically means that the language has the property of referential transparency. He explained it. What we found out when we started to come up with a bunch of use cases and basically bouncing the ideas off of designers, off of artists and whatnot, is that the language feels very natural for the problem domain. It's easy to reason about your setups. It's easy to follow what's going on, where the certain parts of the motion are coming from. At the same time, we expect it to be easy to debug in isolation due to the exact same reasons, because it's easy to reason where the state comes from. It simplifies the workflow, as in it offloads the performance concerns from the user up to the runtime. And from the point of view of the runtime, it's first of all, it's easy to parallelize, or more like it's inherently parallel. It provides us with clear dependencies. There are many well-researched optimization techniques available for that. And it also provides us with a straightforward way to implement state snapshotting, which is also one of the things that Claudio already mentioned. So that's enough with the theory, I guess. Let's go with a practical example. So to build up on the example that Claudio already mentioned for the TPP character, this is essentially what you would probably see if you interact with the animation graph for the first time. So we have this is the default that every character starts with. Let's say you already have your character running a locomotion state machine. This is the graph that it's using. It's very simple. It binds to anything. It just outputs the pose. Doesn't really do anything. Let's say we want to introduce some upper body actions to it. So in this case, we're introducing a new input to the graph, which is essentially like a scope. Then we name them to be able to bind them to different resources. And we introduced a mask blend node to be able to blend like the upper body part from a different source than the lower body part. So one thing worth noting is that when we're designing it, we want the mask blends to be to use soft masks, soft joint masks, which essentially means that the intermediate part of the character skeleton can be affected partially by one motion and the other. So it's not like a binary cut. We cannot, in this particular example, we can have like a medium section of a character skeleton of a character spine which is affected to a certain degree by one animation and the other. All right, then we want to add some additional details, so we do it with an additive blend node. At that point, we want the character to be able to look into a certain direction. For that, we introduce like a look pose blend space, which is also masked on top of what we previously had. It also takes an additional parameter which controls if the look motion is actually blended in onto the character or whatnot, which is controlled by some sort of high level logic. Then we realized that our look pose is actually overriding the detail breathing animation that we introduced previously. So we changing the places. But at that point, the detail animation is obviously affecting the look pose. So we probably want to correct the character to be able, well, by just making him sway. So we probably want to correct the pose, correct the looking direction with some sort of procedural corrections. Let's say we're using the post modifiers called look IK. And we provide additional look target. This more or less reflects the example that Claudio had previously presented. After that, we want to introduce a new feature, which is like a hit reaction. So we introduced additional scope, which is capable of overriding like what we currently have, just to play like a full body hit reaction animation and whatnot. This is a simple example, more or less works. Then we realized that our hit reaction, when we plug it in and out, is not blending smoothly with what we currently have. And this is because we are missing the weight input to the blend node, right? And all of the other examples, we expected all of the inputs to always be present, so it wasn't an issue. But if we're plugging in and out the hit reaction, it just doesn't look nice. So we replace it with a smooth blend node, which is essentially going to provide a way to blend that animation in and out smoothly. And apply some, well, procedural corrections on top, let's say, like we want to physically simulate like a strain of hair or something. So let's talk a little bit about the debugging facilities that we have planned for the graph. So these are all things that are easily achievable with that stem directly from the fact that we went with a purely functional design and are building up on it. First of all, we want to provide a ways for pose inspection at any edge of the graph, so we can run a correct animation, then look at the graph editor, highlight any edge, and you should be able to figure out to see what the correct motion looks at that point. Since there is no hidden state within the graph itself, it's easy to reason about where that motion came from. It's essentially, well, pretty obvious. If you look at the highlighted parts of the graph which are currently active and contributing to the pose you're looking at, and you know there's no like state machines like running like in behind that, it's very easy to just track where parts of the motion came from. At the same time, we want the graph to be capable to be debuggable in isolation through input mocking. And for that I mean, once we have your graph set up, or like a part of the graph set up, and you want to see how it responds to certain inputs, you can just mock in different inputs to it, and maybe bind like some sort of parameter, like a vector or like a blend weight, map it to the analog input of your path, and just see how the graph responds in real time. Which parts become active, which parts become passive, and what's the resulting pose. And finally, this is something already been mentioned, but we really want to provide a way to play back state recorded in the game. So let's say you're observing a game and you're running a game and you realize your character's animation glitches. At this point, you should be able to dump in its the last few seconds of his animation, then load it back in the editor, be able to replay it and inspect it and see where it actually came from. This is a very useful feature for debugging, we think, and it's also easily achievable with the purely functional design, because as Claudio already mentioned, the whole state of the graph is always reconstructible for input, so the only thing we need to do is just snapshot the state of the input samplers, and then we can play it. Then we can replay it, move in time back and forth, and basically see how where the animation glitch came from. Okay, so getting back to our example. Probably have noticed like certain edges of the graph, certain nodes on the graph are marked with a different color than the others. If you think about the implementation details of the smooth blend of physical exchange implementations, they're not essentially stateless, like they hold some sort of internal state. So essentially we have use cases in which we will have to have stateful nodes within our graph, which we don't want for different reasons. And we need to find a way to deal with it. So there's a number of ways we can approach it to actually restore the reflection transparency. The trick that we use is actually based on a couple of constraints that we put on node implementations. First of all is the fact that the state has to be always private. Like if a node has an internal state, it always needs to be private to this particular instance. It can be shared with anything else. It cannot have any side effects. At the same time, the state needs to be able to be derived just from the history of inputs, and it's not interacting with anything outside. So it needs to be like a deterministic function of the history of its inputs. Actually, not as restrictive as it sounds, because, well, you can even use like pseudo-random number generators with this type of approach. So if this condition is met, what we can do is introduce like implicit inputs and outputs to our animation graph. These are completely invisible to the designer. So what does essentially turns our like smooth blend function of any post modifiers that needs to hold a state, introduce like additional input and additional output. So when these nodes are being executed, these are essentially taking two inputs and outputting two outputs. The outputs then being stored for the evaluation in the next frame. So essentially what's happening right now is that the implementation of the node is offloading its internal state into the framework, so we can manage it. So for all intents and purposes, this is essentially like a syntactic trigger from the point of view of the programmer or user of the language that lets us, well, basically treat all the nodes in our graph as referentially transparent. All right, but let's say we have a case in which we want to interact with some sort of external system and incorporate that into the graph as a part of our computation. Well, this is getting a little bit tough because we can't really reuse the previous technique, as we cannot constrain arbitrary systems to the same degree that we are constraining like simple node implementations. In this example, we have some sort of physical post process that needs to have the character pose being fed to it, evaluate whatever it's evaluating, and then we also want to blend in with the result of that simulation back to output it back to the character. All right, so this is quite tricky actually. One of the ways we can approach it is by delaying the physical simulation by a single frame, but in certain cases it might not be acceptable. We want to support this particular use case without frame delays in the general case. All right, so what we can do in this particular case? Well, there's a bunch of very elegant functional tools for dealing with state and input-output, but it quickly became apparent for us when we were experimenting with them that they are unfeasible to use if we can't reschedule updates of other systems within the engine. So when working within a highly imperative framework of the engine, it's just unfeasible to be using like functional approaches to that. So the practical solution that we came up with is essentially to split the program into subgraphs. In this particular case, we'll be basically splitting our whole animation motion synthesis program into subparts. The first part that feeds into the unpure node will be evaluated first at the earliest time and frame it is possible. And then we'll store it results somewhere. And then the other part of the graph will wait until a synchronization point within the frame when the physics update actually finished, and it will just take like the result of it and just wrap it up while putting the final corrected pose. So what we're essentially doing is we're scheduling like different parts of corrector. One of the benefits that we have of having referential transparency within our graph is the fact that we can schedule updates arbitrarily. We can split our updates into as many parts as we want. It's very useful for workload management in general, especially if we are working within a framework of the engine that has these synchronization points like pre-physics updates, post-physics updates, and whatnot. Internally, we went through a lot of practical use cases, and we were basically exploring a lot of different possibilities, talking with a lot of people. And what we managed to restrict consistently is that, we're working with a purely functional DSL, which is pretty huge at the very least, with some syntactic sugar on top, but it doesn't matter. We also managed to restrict that every single function node always has just a single pose output, which is going to be useful in a second. Also, we realized we don't really need recursion, or from the data flow perspective, we don't need like feedback loops. Essentially, there are certain features that may actually use it, but for the time being, we didn't really find like a practical use case for that. So this is something we might explore in the future, but for the time being, we are perfectly fine without having that. And so essentially what it means is that our whole motion synthesis program or the graph is expressed as a directed acyclic graph, which for all intents and purposes can be thought about as a tree. It's essentially like an abstract syntax tree with some common sub-expressions collapsed together. This is where the actual nerdy part begins, so I'm sorry for that. Our goal right now is essentially, once we have this DSL, our goal is to efficiently compute the outposts, and to do that we introduce a computational backend. So our computational backend consists of a very lightweight SIMD library, which is tailored specifically for 3D algebraic structures. It has a parameterizable stride, which in practice means that we'll be crunching like 4 or 8 quads at the same time, depending on the CPU architecture. And what that also means is that memory locality is going to be imperative for efficient computation because we are memory bound already from what we measured. We are performing very simple operations, like linear blendings are extremely simple operations, but at the same time we're going through like vast amounts of memory at the same time. So what we want to do to squeeze out performance of this particular model is just to increase memory locality. And to alleviate that, we introduced a data structure which is tailored specifically for holding sparse character poses. And joints in this, basically joints are, this is a data structure with joints, like character bones are represented by channels, which are densely packed within the storing buffer. They also have consistent ordering between like different buffers that interact with each other. So that basically guarantees sequential memory access if we are iterating over certain buffers or matching channels pairwise. Then there's some allocation mask on top, which just describes like the structure of the densely packed buffer, and this it is used for shifting and unshifting values into the SIMG register. There is a logical mask on top, which basically describes which channels are actually logically contained in the buffer and whatnot. And the duality of the allocation mask and logical mask basically allows us to make the buffers resizable up to what the allocation mask provides. The reason we want them resizable is obviously because we want to reuse these buffers for, well, more temporal locality and to have less cache pressure in general. We have sequential locality, which is provided by the post buffer data structure, but we still want to maximize temporal locality, which is why we need to devise a smart algorithm that comes with a strategy for optimal buffer allocation and assignment and reuse. So what do we have to work with? We basically have like a graph of pure functions that produce exactly one output and take at least one pose input. The conclusion here is obvious. We can always reuse one of the input buffers as the output buffer, which is pretty powerful. To address that, we were basically proposing a 2-pass evaluation algorithm in which the initial pass is only used to determine like the optimal buffer allocation and reuse strategy, and the second pass will perform the actual number crunching. Right, so let's give this one. So coming back to our previous example, if we look at the structure of the graph that we presented previously, we can essentially say that we only need 2 buffers, which are marked with the colors green and yellow on the graph, and this is more or less sufficient to evaluate the graph that we presented previously. We're obviously disregarding like the scalar parameters because they're not really relevant right now. Only the poses, so the heavy data structures not here. So the first pass of the algorithm, which is supposed to just assign the buffers, is basically going to be like a depth-first traversal of the graph, in which we start from the output, then we go up, basically specifying, assigning to every edge like the amount of data that we expect to be delivered, and then on the way back, when the traversal goes back, like the producer buffers can actually adjust the size of the edge of the graph depending on what it can actually produce. So we can consider like every edge on the graph to essentially be like a meeting point between a consumer and producer, where they can negotiate what data is actually needed and what can be delivered. So in this particular example, those 2 buffers, we need to have the sizes of full character pose, and that essentially stems from the fact that we have this hit reaction edge at the very bottom, which is a full body animation, and we can't really do it. So the smooth blend at the very bottom is basically the case in which we are blending like the two full body animations together, so we cannot really go lower than that. What's also worth noticing is the fact that due to like the inherent masking of certain nodes, like the mask blends, like certain edges are much lighter than the other. But if the hit reaction input is not plugged in, you can immediately see that the requirements for the second buffer are much lower than this, so that essentially reduces the cache pressure a lot. And for instance, if we introduce like a LOD level, which is represented by LOD mask, we can see how like the memory requirements of the whole graph go down, but at the same time, it also reduces the workload of all the input nodes. So for instance, the locomotion upper body samplers right now will know they will only need to deliver like 19 or 28 joints instead of the full character pose, as they were providing previously. The cool thing about the LOD mask now is the fact that if you think about this, essentially no up when it comes to pose evaluation, it's only meaningful during the buffer evaluation pass. Once we have this, how we can actually reduce the cache pressure even more. So let's talk a little bit about the node API. So to abstract away our vectorized pose buffers that I talked about previously, we introduced like a simple API for implementing nodes within our graph. So for parent space operations specifically, which is the main use case for most of our nodes that we are implementing, we're providing a bunch of higher order functions. Essentially what they do is they iterate simultaneously on a number of buffers provided, and applied some sort of user-provided function whenever they are matching the channels between them, and evaluate the user-provided functions. So this essentially assures sequential access in general when iterating over these buffers, and it's pretty cool and handy for developer in general. The other thing is the fact that we can also leverage that on our end, on the end of the runtime. And this is essentially when we're reaping a lot of benefits for the reflection transparency when it comes to performance benefits. So let's take a look at the same API from the point of view of our functional language. So first thing that we can figure out is the fact that the sparse stream data structure that we are using within our poses is actually what functional programming refers to as a functor. If you're unfamiliar with functional programming, a functor is essentially like a structure that wraps some sort of a type and then provides a way to apply functions on top of itself that were originally designed only to work on the base type. And that wrapping essentially is, the purpose of the wrapping is to introduce some additional computational context. So, for example, in C++, a vector can be thought about as a functor, because you can map a function over, and in the case of a vector, like the additional context is the fact that the function is applied on every single element of that, or an std optional, in which the additional context is the fact that the function might be applied or not, depending on if the std optional holds like a value in itself or not. What's important is the fact that the provided function itself is not aware of that context. Like you don't have to concern, like the implementer of the function doesn't need to concern himself with the thing. And in case of our sparse stream buffer specifically, we can realize that our sparse stream template is essentially like a functor over an arbitrary type, in this case a quad. And the computational context in this case is that element-wise matching of post channels when applying this function. More general way of to think about a functor from a point of view of functional programming, equivalent but more generalized fact, is that a functor takes a user-provided function and then elevates it into some sort of morphism that can be applied onto the wrapped sparse stream type. While having only functions that can only work on quads, by elevating it, we can apply it directly to the sparse stream wrapper of the quad type. So we don't really need it in C++. It's just here to picture the idea. In most functional languages, like the syntax for both of these is actually equivalent. So why is it useful? So it is useful because we can do graph transformations with it, as in we can capture user-provided lambdas, and then combine operations together to achieve less buffer traversals when executing like user-provided functions. Let's consider a simple subgraph that you would want to transform. So let's say we have like this particular use case in the part of our graph when we have two binary functions combined with sequence one after each other. And what we want to have instead is basically like a single ternary function. The benefit here is the fact that instead of doing 4 iterations in total over 3 buffers, we're only doing it in a single pass by only having 3 buffer traversals. We have the lambdas provided by the implementer. Now we can compose them because they're pure functions. The nodes within our graph are essentially not these lambdas. These are like some sort of morphism which are capable of working on the post buffers, which are generated from the user-provided lambdas. Since we know that the post buffer is a functor, or more specifically, it's a special case of functor called applicative functor, that means we can combine them exactly as we would combine the functions. All right, so let's do some substitutions, remapping, partially applying arguments. So essentially, like the form that we want to achieve after applying a couple of conversions is this functional composition form. In this case, we basically have like 2 partially applied functions that we have combined together into a single computational object that we apply to the A buffer. So what it essentially means, if we expand it, is that we have this type of form. If we make the runtime execute these particular nodes in this particular fashion, it essentially means that we'll be reusing the A buffer as the output, because all of the other stuff is just like compositional functions that we can apply directly. We can actually reuse any buffer as the output. So this is the example when we would like to reuse B. In case of C, unfortunately, we can't really do it. Because it has some sort of sub problem, like a sub computation that we cannot really expose in terms of function composition. So this is not that big of a deal, honestly speaking. But the problem is the fact that we'll need to store some sort of intermediate result of that computation, which is only for a single quad. But at the same time, it complicates the algorithm quite a bit, and also increases the register pressure. So this is not something we'll be exploring for the time being. We're mostly focusing on the function composition cases. Since, well, it's extremely simple to implement on the backend side, and at the same time covers a lot of use cases. Like if you think about the example from before, a lot of use cases for the animation graph is essentially like incremental blending on top of what the previous post have already been providing. So just applying this is probably providing us with a lot of benefits already. Just to quickly go through a couple of examples, like for instance, if you have a unary operation, and which is applied on top of binary operation, which is an extremely simple case, obviously. I mean, it's pretty obvious that this comes for free, because while executing f, iterating with the buffers, we might as well just execute g, and scales with any number of unary functions. This is like a trivial example. Then we have structure like this, for example. We run into a problem that we also have like a subcomputational problem, but at the same time we're reducing the number of buffer traversals by 50%, so it's probably beneficial to have it anyway. And just to give like another example, this is basically like an expanded use case of what we had previously. So this thing scales very well. There are like well-known approaches to actually transform these type of expressions into something that's actually consistent purely of function composition. All right. So the question is this actually beneficial for performance? And the answer is, well, we don't know because we haven't measured it. We haven't implemented it yet. What we do know though is the fact that our computational backend at this point is extremely memory bound, mostly because it consists of very simple operations and operates on vast amounts of memory. So we suspect that it will be these type of transformations will provide significant performance benefits. And even if not, like it's still like nice to have a bunch of options that we can explore and see how it actually reflects when it comes to runtime performance. Other related ideas that we are thinking about exploring is essentially, well, in case, let's say, we're combining multiple blend operations together, and we know they are only blends. In that case, we can replace like this type of structure with a specialized node. For instance, in this particular case, we will be able to skip quaternion normalization, which is like the heaviest step of interpolation, and just apply it at the variance. So in this particular case, we'll be able to replace like a whole structure like this, with a specialized node that's like just good approximation of multiple sequence and lerps, and it's much faster at the same time. So we already do it for blend spaces, so we know it actually works. We can also experiment a little bit with memory layouts, maybe try to interleave like buffers, which will be executed together because we have these functions that consume 5 buffers at the same time. So maybe we want to interleave them like in sequential memory order to be able to provide even more sequential access patterns. Well, that depends. We'll still be optimizing it. So in conclusion, we presented a modular playable system, which is the part that Claudio covered, which scales very well with large games because of full flexibility and high reusability of setups between characters. We've also introduced an animation graph DSL, which serves for motion synthesis, which serves as a computational backend for the whole set. And we expected to scale very well with computational workflow and with complex character setups because of reasons that I already explained.
All right, thanks guys.
Achieved with CRYENGINE.